Okay, so this last section deals with something we call continuity. And it's really kind of easy to visually see what we mean by continuity, so we're going to start there, of course. So if I have a nice, simple polynomial function of x squared, okay, I can take my pencil and I can trace this function without ever lifting the pencil or anything, correct? This is what we would call, makes sense, word continuity applies here. This is a nice continuous function at every single point. Doesn't have any breaks, right? Now, we've learned that the function which seems like a crazy function, right? X squared times x minus 1 over x minus 1. What have we learned about this function without even putting the word limit anywhere? What is something you could tell me about it? Yes, there's an issue. Like we talk about issues, right? If I plug in 1, I have an issue, right? Because I'm going to get a 0 in the denominator. But why is it not a vertical asymptote? Because the x minus 1 term cancels. Right? Isn't that pretty much the same as just the previous function? Except for one little thing, it has a hole. So notice that x squared x minus 1 over x minus 1, is not the same function. When you sketch this one, you have to know to do what? At 1, I'm going to exaggerate the hole. All right, that looks a little weird, but you get the idea. Okay, you're not going to see it on Desmos, right? You wouldn't see it unless you did what? Took your little pen, your cursor, and then it said, oh, it's undefined there. Does the limit exist at 1? Absolutely. The limit exists because the right-hand side and the left-hand side are going to the same place. Remember, we talked about this first class. Don't forget it. We're prepping for a test next week. The limit exists at 1, but you don't have a value at 1. You have a hole. So these are the things you want to remember as you're going through everything. Is it continuous at 1? No, because what would happen? I have to lift my pencil to continue the function, right? That is not a continuous function. At 1. Is the function continuous at the point x equals -1? Yeah, it's fine at x equals -1. I can go through there. So when we talk about continuity, there's different ways to talk about continuity that we'll write down. But for now, just think about it. You could be continuous on an entire interval. We're going to also look specifically at continuity at a specific point. So if I wanted to know what was happening at 1, my function's not continuous at 1. It actually has what we call removable continuity, meaning it's just one little point. If I were to put it back in, plug it up, it would be continuous, right? But it's not continuous. It is continuous at -1. It's continuous everywhere except at 1. Okay? So that's one type of a discontinuity. All right? Let's take a look at another one. This is called your piecewise function. It's one function up to a certain point, and then it's another function after that point. That's your piecewise function. Where's the discontinuity occurring? At 1. Now, my function has a value at 1. What's my function's value at the number 1? 1. It has a value at 1. Definitely has a value at 1. All right? Is it continuous at 1? No. It actually has what we would call, it has some left-hand continuity. It's continuous great when you're coming from the left, right? but it's not on the other side. So we have a discontinuity. This one is non-removable. Do you see the difference? This one is a removable discontinuity. Basically, removable as a whole. You can take your finger, plug it up, you'd be continuous. All right? This one we have a not, and definitely not. Does the limit exist at 1? So there's a lot of different things that can occur. Does the limit of my last graph, does that limit exist at 1? Nope, because the left-hand side doesn't equal the right-hand side, remember? Limit doesn't exist. It's non-removable. In a removable discontinuity, guess what? The limit does exist. Okay. Other differences. In my removable one, the value doesn't exist at 1, right? You can't evaluate the actual function at 1. Can I evaluate the function of my piecewise? Yeah, I can evaluate it, but the limit doesn't exist. So there are a lot of different things to remember when it comes to continuous functions. So we're going to talk very specifically about continuity at a point. No. Oh, no. There we go. So a function f is continuous at a if the limit as x approaches a is actually equal to f of a. In order for a function to be continuous at a, the limit as x approaches a of f of x has to equal the same value if you were to plug a into it. So if you come back, here, we'll go to this function. We'll go to -1. We'll call this function h of x. Is h of x continuous at -1, do you think? So is the limit of h of x as x approaches -1 continuous? What do you think? Function is continuous at a if the limit as x approaches a of x actually equals f of a. Is it continuous at -1? Looking at the picture. Yeah, I can take my finger and go right through -1 and not move, right? Yeah, it's actually continuous at -1. Okay? But you're not always going to have the graph, right? So what we're going to develop real quick is a short 3-step checklist. It's going to seem a little redundant, but guess what? When I grade the lab and do the test, what do I want to see? The 3-step checklist. So it's actually called the continuity checklist. So how are you going to determine for sure that your limit, that your function is continuous at a point? We're going to go through our continuity checklist. So based on that definition, here's the first one. So I'll write, let me do this too. In order for f to be continuous at a, all 3 conditions must hold. Not one, not a majority, all 3. Here's the first one. Well, f of a must be defined. Meaning a is in the domain of f. Okay, the function has to exist there. That's number one. You got to be able to take that a and just plug it into your function. Notice there's no limit there. Okay, you must be able to do that. So when I look at our three examples, you have them in your notes. I don't want to move this yet. Some people are still copying. First example, the parabola at 1, it's fine. Defined. You would check off number 1. You could plug in 1 to x squared, and you're good. When we check it's defined, you have to have your original function in non-simplified form. That's important because, I got to move this 1 second. Take a look at this example over here. This one. Can I plug 1 into the original function? No. Okay? F of a is not defined. You can't plug 1 in. So right away, you would, on that function, you'd fail your continuity checklist at 1 because you wouldn't be able to plug 1 in. You wouldn't even have to do number 2 and number 3. That's what's nice.
So once it automatically fails,
you're finished. Yep. Yeah. So that's what's nice about the checklist. As soon as you fail the checklist, you don't have to go on to the next step. What would happen is, suppose we were doing all of these at 1, right? That one would check. This one would automatically fail and you'd be done. Because this, and this is where it's important, you got to plug it into the original function before you simplify the original function. It fails, right? It's not defined. You'd be done. Here, yeah, you would get through step 1 because that would be there. You'd have a value for that function at 1. Okay? All right. Step 2. The limit must exist. This is a tricky one. The limit as x approaches, whatever that value of a is, it's the same for all the whole checklist. I'm going to add to this because it says, oh, the limit, to remind you of a very important thing. For a limit to exist, what must be true about the two sides? You got to be the same. And that is the piece you often have to check here that students forget to check. That means the limit as x approaches a from the left has to equal the limit as x approaches a from the right. Because you'll think the limit exists, but it doesn't. Okay? So we'll go back up to those 3 examples again. All right, and I will put this back up. So we know the first example here, it checked. Does the limit exist at 1? Left and right come into the same place? Checks again. Now, this one, it already failed the first one, right? So we wouldn't do it again. But do you see if we were to, suppose we didn't realize it failed, and that is a common mistake because you accidentally plug it into the simplified thing, right? Does the limit exist? Yeah, it would actually bypass number 2. The problem is it didn't bypass number 1 in the first place. Now, remember this piecewise function. F of a, f of 1 is equal to 1. It's defined. It checked it checked number 1. Does it check number 2? Does the left equal the right? So this one would fail on number 2. Okay? So far, number 1 passes both. First one failed on 1, the third one failed on 2. Okay, what do you think the third thing is? Or, before you answer that, let me show you a function that actually passes both 1 and 2. a different function than what I've given you already. So I'm going to give you this function. Let's suppose it's similar to what we already had. Let's do wasn't that our second function? And I'm going to define that for all values when x is not equal to 1. Okay? So I'm going to create a piecewise function. And now I'm going to go ahead and I'm going to say that, hey, wait a minute. This function's going to equal 2 when x equals 1. I can define that function. It's a perfectly fine function. Let's see what that function looks like. Okay, it, boom, has really big hole. Okay, right at 1. It's got that hole at 1. And if I, right here on the graph would be the number 1, but it has a hole there. So I'm going to go ahead and say, oh, but at 1, I'm going to put a dot right there. See what I did? Everybody see it? Okay, let's go through the checklist on what we have so far. First checklist says, when I look at that piecewise function, is it, sorry, I can't put it all in here at the same time, is f of a defined? Meaning, I want to check this function, I want to check continuity when a equals 1. Well, is my function defined when a equals 1? Yes, I have a value. What is the value when a equals 1? So, if I'm doing my continuity checklist, I'm good. F of a equals 2. I'm a defined value. Does my limit exist at x equals 1? Can I do the limit as x approaches 1 of f of x? Sure, look at the graph. The limit exists. What is the limit? It's approaching what value? 1. Everybody see that? The limit exists. The limit approaches 1. Because when you're finding a limit, you can cancel those x minus 1s and plug in 1 and you can get, the limit exists. When you look at the graph, would you call that a continuous function? Remember, continuous means I can leave my, do I have to lift my pencil? Yes. Would you call it a continuous function? Right? Up, down, boom. Not continuous. Everyone agree that is probably not continuous. What do you think my third step is? Want to take a guess? Because that checked 1, that checked 2. We need something to catch that situation. Any guesses? Go on. Not the squeeze theorem. Noticed the function's value was 2, but the limit was 1. In order for it to be continuous, what they have to do, what? Equal each other. So the third thing is simply the limit as x approaches a of x is f of x has to actually equal. In other words, whatever you found in step 1 has to equal the same thing you found in step 2. And that's it. That's your checklist. But to do that, because you might be sitting here, well, that's obvious. No, it's not. I can adjust my piecewise function to make this continuous by doing one little thing. If I didn't call that a 2 and I called that wouldn't I have a continuous function now? Yes. So this is where some of the problems in the lab come in. They let you say, all right, here's part of your function. What would have to be in this place in order for you to have continuity at x equals 1? So you get to play around with that a little bit, okay? So I'm going to stop the continuity discussion here. This is the bulk of it. There's a little minute details that we will go over on Thursday because I want you to jump into the lab for the last 35 minutes, okay?